In this video, I will show you the process that I am currently using to model a Revit family that has faces that can be moved or directed in any angle that the user wants. First of all, I'm going to sketch the family quickly so you can understand the function of the family. The family is actually a rectangle. We have here a rectangle that has faces that can be set by the architect in any angle that he desires. This family has a secret purpose that I won't show in this video, but that is the function of the family. Of course, here we need to solve the corners first. This is a trick, solving these corners, but this is going to be a task to be achieved later. I already have a solution for this, but here I want us to focus on how to create these faces that can receive any angle that the architect desires, even if the angle can be set in the opposite direction. This is quite complicated because you can see that the angle can move the lines, the length of the triangles of the faces in both sides, in the upper line or in the bottom line in the case of the face. So it is a pretty good exercise of analysis and family modeling. So let me show you how we are going to proceed. The first thing that we need to resolve a family like this is actually understanding really very well the theory. You need to understand the theory behind the calculations. You need to understand the theory in order to produce a formula for the Revit parameters in order to make the family work. So you need to understand the mathematics. These mathematics are really simple. It is just Pythagoras theorem. It is actually quite simple. So in order to show you how to do this, we're going to make a bunch of exercises in Revit. I want you to understand how does the theory is used, so then you can do the work of translating this theory into the Revit family. And actually, I am recording this video because I want to have a video so I can remember after, because maybe I can forget many of these things. So this is going to be good. Here we have faces in each side of the rectangle that is going to be the core of the family, and we are going to resolve the distance that the longer line has to obtain to produce the angle. The architect is going to provide the distance of the length and the width of the box and the angle of the face. He's going to give us this parameter and this parameter to construct the angle. But we need to figure out the length of the line that is going to move the triangle in order to create the angle that the architect is specifying. So this is the exercise. We are going to resolve the length of the lines that I put in red in order to make this family fully functional and parametric. So let's go with this one first. Let's draw a simulation over here. First, I'm going to write the magic words. The magic words are so Toa. This is actually a technique that I learned today using Khan Academy. The Khan Academy websites and videos, they are so good, and I am using them to learn this theory right now. So here we have the face of the rectangle. We have the height of this face. We know that it is 40. This is 40. This can be made in any unit. If you are using feet, you then have to convert it, but that is pretty easy. I can show you later. And you have this angle. The architect is going to provide both of these parameters and you need to define the length of this line that we are going to call x. And the angle is 70.392. 70.392. Okay, I told you that these are the magic words, and these are words to remember the theorem of Pythagoras. This basically means the sine is the opposite side between the hypotenuse. The cosine is the adjacent side between the hypotenuse, and the tangent is the opposite side between the adjacent side. And this solves our problem. The problem is that we need to obtain this line over here, and we have the height of the triangle in this case, in this orientation. So this is going to be easy because we know that we have the opposite side to the angle, and we need to find out the adjacent side of the angle. So the one of these formulas that has both sides and can help us is this one, TOA. Actually, this is the one that we're going to use for every case. And this formula what says is that the angle, the tangent of the angle, that the angle is 70.392 is equal to the opposite side that it's 40 in this case between the adjacent side that we are going to call x. And here we already have solved the problem, because we know that we need to, in order to transform this equation, we need to multiply both sides by x, right? We need to multiply both sides by x in order to cancel this fraction. So we get that x per the tangent of 70.392 equals to 40. So here we are going to do another operation. We are going to multiply both sides, we're going to divide, both sides by the tangent of 70 in order to obtain x here in the left. And this is going, when we multiply, when we divide this value, this is going to eliminate the other one, and we are going to get the result as we see here. X is equal to the tangent, to 40 between the tangent of the angle. So now we're going to calculate what we have here. We will calculate first the tangent. Let's put over here 70.392, and let's ask the calculator for the tangent. Okay, this is 2.807. 2.807. Okay, 40 between 2.807 is equal to 1425. So x equals to 1425. This is our result. Don't worry, I understand that this may seem complicated. I don't think that I explained it quite well, but I'm going to explain it many more times so you can understand. Okay, this is our guess. Let's see if it is correct. Let's measure this line, and the line has a length of 1425. Did you see? What we need to do is actually create a formula that can perform this operation in each phase of the Revit family. And this is the way that we're going to obtain the length. In the next videos, I will continue to practice this method.